Hi everyone. We're going to focus on semiconductors as well as polymers in this video, and then we're going to go back toward chapter 11 and kind of finish up our properties of liquids and also talk about heating and cooling curves. So in semiconductors, or actually let's just define what a semiconductor is first before we get into what this slide is talking about. Ultimately, a semiconductor is a material that has an electrical conductivity between a conductor and between an insulator. So a lot of semiconductors today are really just the foundation of technology for us. So we see them in a lot of different types of electronics. Now, our semiconductors, where would we be able to find them if we're thinking about just elemental semiconductors? A lot of them are going to be in group 4A, which is that carbon family. So a lot of the covalent network solids would act like wonderful semiconductors, and I'm going to be specifically focusing probably most on carbon and silicon. Germanium can also be a good semiconductor, but tin and lead are not so much good semiconductors, and we'll talk about why in just a second. With semiconductors, we can utilize different types of semiconductors just because of their movement of electrons. Now, group 4A is special in that we know it can gain 4 electrons to fulfill its outer shell, or it could lose 4 electrons. So I think just because of the fact that it has those 4 valence electrons and it has the ability to gain or lose, that's really what makes these the perfect semiconductors, because it just gives them that ability to gain and lose electrons equally at the same time. Now, how can I describe, or how do I, at the particulate level, really think about semiconductors and how they work? We go back to the Mo theory. We go back to molecular orbital theory, okay? And a lot of this stuff is just found experimentally. Semiconductors is a newer type of topic for us. We really only started semiconductor work in the 1980s. And then since the 1980s, it's kind of exploded into different forms of technology that we've seen. So with carbon and silicon and germanium, if I think about their molecular orbital diagrams, if I think about their MOs, remember that we called the ones down here with the lower energy level, those are the bonding molecular orbitals. And then as I increase in energy here, if I'm looking at that y-axis, the ones that are higher in energy is going to be that anti-bonding molecular orbital. So we give them another name when we talk about them in terms of semiconductor form. So the bonding molecular orbital, they call that the valence band. And then the anti-bonding molecular orbital, we're going to call that the conduction band. The reason we call it valence band is because we're trying to show these are the ones that are actually bonding. These are the ones that are going to bring things together, versus the anti-bonding, we call that the conduction band, because if you don't have any electrons in those anti-bonding modes, we have found that that is what's going to make the best semiconductor. If I start adding electrons into that conduction band, I'm going to start to see that I lose some of the integrity then of the strength of the bonds that we're talking about. And then that semiconductor capability is going to go down. So it's going to act then more like an insulator than it would act like a conductor. With the valence band and the conduction band, another thing that is important in determining if something will be a good semiconductor is the gap of energy between these two bands. What's the gap of energy like between the bonding molecular orbital? What's the gap of energy like between bonding orbital and then that anti-bonding orbital, the conduction band? If we think about it in terms of carbon and silicon, both of them are pretty small in terms of their, if I'm comparing just down that column, that 4A column, carbon and silicon smaller in their atomic size, so their overlap isn't going to be nearly as great just because they're smaller in size. As I move down that column, as I move down to germanium, to tin, to lead, the atomic size gets larger. And because that atomic size gets larger, I can see that overlap is also going to do something different just because the atomic size is bigger. So because of that, because atomic size is bigger, and because there's a weaker Coulombic attraction, probably since I'm increasing shielding, increasing energy level, that band gap, the energy between the bonding molecular orbitals and the anti-bonding molecular orbitals is going to get smaller. So because I have a smaller gap here, it's just going to tell me that it's not going to be as good of a semiconductor. So the larger the band gap between that valence band and that conduction band, the better the semiconductor. And then I can also say, as soon as I add electrons into the conduction band, the worse the semiconductor is going to be. It's going to act more like an insulator, okay? So this is just how we try to determine how well a semiconductor will work based on that particulate level, which is just us using the molecular orbital theory. So we see that group 4A have the best gap, or the largest gap, between valence band and conduction band. So this is the reason why we say that they're the best semiconductors, because experimentally we have seen that if this gap is large, they will do a really good job in terms of conducting. And again, I believe, and scientists would believe, that it's because they have that ability to gain and lose electrons very easily, and they can do it pretty much simultaneously, so it makes them a really good conductor or semiconductor. Okay, again, this is just saying the same thing. Among elements, only group 4A, all of which have 4 valence electrons, are semiconductors. So there are two main types of semiconductors. There's elemental semiconductors, and then there's also just inorganic compounds of semiconductors. So an example of that could be GaAs. And as long as on average it's like they're going to have 4 valence electrons, then we will say that it will act like a semiconductor. At least that's, again, what we've seen experimentally. So this little set of elements here are ones that can act like semiconductors. And then table 12.4 in your book is just showing you some different elemental types. So here's silicon,